Chapter 2014, and I'm going to solve this problem. Find the values of p where the sum converges, and this is our sum as k is from 2 to infinity, 1 over k times the natural log of k versus p. The first thing we need to, best way to do this is using one of the convergence tests. One I'll be using is the basic comparison test. Basically what this is using a function that is similar to this one and comparing its end behaviors to find out whether or not it converges. So to pick a function, first we have to set this. Let a of n be 1 over k ln of k. A similar function to this would possibly be 1 over ln k. And we set this to be. Now, first we have to figure out whether this is bigger than this, or vice versa. Well, using a simple way, we could say since this function is being multiplied by something, like naturally when you have a fraction such as 1 over 2 and 1 over 2 times 3, this would be bigger, because when you multiply this, you have 1 over 2 and then 1 over 6. And we all know the 1 over 6 is smaller than 1 over 2. The multiplication makes the denominator bigger, making the entire number itself smaller. So that's why this is bigger than this. Then we said that b of n is greater than a of n. We would kind of expect it to converge. The rule says that if like this is bigger than this and this converges, then this converges as well. But then we have to figure out how it would convert, how b of n, 1 to the natural log k raised to the power p, would converge. Looking at this, we can't really determine because p, we don't really know what p is. But if we use the p series test, we can figure out where it converges. Here's the p series test. Basically states that if p, which is an exponential on a function, is greater than 1, then the series converges. And p is less than 1, the series diverges. And if p is equal to 1, it also diverges. The reason why is if you have something like, let's say 1 over k to the p. If k is 2, and let's say p is 2, when we look at the behavior of this, it would go like this, and it converges to 0. If k was negative 1, we would have k, and that obviously just goes on and on and on to infinity. If we have k is 1, that'd be 1 over k, and using 1 over k, it goes kind of like this, and it just needs to go on. So using this, we know that b of n converges when p is greater than 1. Therefore, by the basic comparison test, a of n would also converge. Now, if p was greater than 1 or equal to 1, we would not be able to test whether or not it converges or diverges. And the reason being that is because if we have B of n right here and A of n right here, the thing is you can only tell it converges because they're similar and the way they move. But if A of n diverges, we wouldn't be able to tell because the most simple way to explain it is by using x squared. For example, a function let A of n be x squared. We got x squared, and we've got x to the power 4. We have this. If this converges, this would also move too. But if x squared diverges, we don't know whether this converges because it would move such that like it would go off, and we don't know what's happening in the middle area.